Hi, welcome back to Derivability. This is the channel where we take a look at proofs, derivations in physics, engineering, mathematics, usually at the introductory, kind of mid-level maybe in undergraduate education. So we're in the middle of a series on hyperbolic functions right now. Hopefully you've had a chance to see the first three. If not, check out the channel. Okay, right now we're on number 4. Number 3 was on derivatives of hyperbolic functions. Okay, number 4 is going to be on integrals. Okay, and just like everything we've been doing so far, maybe you're noticing that what we're finding to be true about hyperbolic functions is it has a very close parallel to what is true about trig functions. Okay. So once again, if you've seen the previous video on derivatives, those two facts that I already have up on the screen for us right now are just very straightforward. The first fact follows from the fact that the derivative of the sinh function is the cos function, okay, and actually vice versa. So very straightforward. We can just paste those almost literally from the previous video. Okay, now don't get me in trouble with your calculus teacher. I am not writing the plus c arbitrary constant on the ends of these. I think we can all agree that those really are there. But I'm just not going to write them. Okay, so next let's take a look at the integration of the hyperbolic tangent function . Okay, and if you know how to integrate just the plain old trigonometric tangent function, this one is very similar. Okay, sinh over cos, like that, and this is very straightforward to do with a substitution, a u substitution, excuse me. Okay, that u substitution is going to be u equals cos x du, then is going to equal sinh x dx. Okay, we know that derivative from the previous video. Okay, and this becomes, okay, that part is the du. Then we have du over u. So of course this becomes the natural log of u. All right. Or the natural log of cos x. Okay. All right, so there you go. I think that's almost identical in almost every way to the circular trigonometric integral. Okay. Now if we do the same thing for the hyperbolic cotangent function, okay, we're going to get something very similar. Okay, so I'll tell you what, if you buy this one, then I think you are going to believe this one as well. You just do the very same sort of decomposition, you might say, of the cos function, cos over sinh, same u substitution, and there you go. Okay, now where the real work is going to happen in this video is going to be the integration of the hyperbolic secant and the hyperbolic cosecant functions. Okay, so let me create some clean space and we'll get right back to that. All right, let's take a look now at the integral antiderivative of the hyperbolic secant function. Okay. All right, now there might be more than one way to do this. I'm going to show you 2 ways. All right. Okay, so the first way, number 1, okay, is I'm going to write this, well, both ways are going to look like this, 1 over the hyperbolic cosine function. Okay, and then let's just remember that the hyperbolic cosine function has an exponential definition. All right, that we talked about in the first video. You may be familiar with that already. Okay, I'm going to put the 2 up in the numerator and also outside the integral. Okay. All right, so now what I'm going to do is I'm going to multiply through top and bottom here by e to the x. And of course, they'll be going inside the integral. Okay, something like that. All right, so what we're going to have here is a 2 on the outside integral, e to the x dx. And then downstairs, denominator, we're going to have e to the 2x plus 1. Okay, now if you kind of have a suspicion about this looking a certain way, let's just make a u substitution. Let's make the substitution u equals e to the x. And of course, du is going to equal e to the x dx. Okay, when we do that, we're going to have a 2 on the outside still. Upstairs, du. Downstairs, u squared plus 1. Okay, now this you might say calls for a trigonometric substitution, but you may already know how this goes. The antiderivative here is the arctan, or the tangent inverse function of the variable u. Okay, so taking this back to the variable x, okay, we get 2, and then tangent inverse e to the x. Okay. Okay, now that's a perfectly fine way of doing things. Okay, but here in a moment I'm going to show you another option, okay, that makes use of some hyperbolic function identities. I think maybe we talked about in our first video, but are otherwise well known. So once again, let me create a little space and we'll get back to it. Okay, let's try a different version of this now. Okay, we start off the same way by talking about hyperbolic secant as 1 over the cosh function. Okay, and what I'm going to do is I'm going to show you a cosh double, sometimes called double angle identity. X here is not an angle. Sometimes it's still called that. Okay, if you want to call it a double argument identity, okay, because X is the argument of that function. Okay, and what we have here is a sum of cosh squared x plus sinh squared x. Now really what we have going on here is cosh of x. So what I'm going to do is I'm going to write that as cosh squared x over 2 plus sinh squared x over 2. Okay, so let's put that in our denominator here. Something like this. Okay, there we go. Now what I'm going to do is I'm going to do a multiplication top and bottom of this integration in order to, once again, put this into kind of a convenient format. So let me multiply top and bottom here by hyperbolic secant squared of x over 2. Okay, and this may seem like a bit of madness at first, but I promise it's going to work out. Okay, so we have the integral. Okay, upstairs, hyperbolic secant squared of x over 2 dx. Now downstairs, what we're going to do is we're going to distribute this in to both terms. Okay, my first term is going to be a 1. Okay, cosh and sech are reciprocals, so that cancels to 1. Okay, the second grouping here, this is essentially the same thing as having sinh squared over cosh squared. So that's the same thing as hyperbolic tangent squared of x over 2. Okay, now once again, you may be kind of getting a feeling about this, thinking, you know, this maybe this looks like we could do some sort of u substitution, and that's exactly what's happening. In fact, it's the same sort of substitution as last time. The same result anyway, not the same substitution. So I'm going to let u equal tanh of x over 2. Du, okay, we're taking a derivative here. Okay, I think we learned, and if you watched the last video, that du is hyperbolic secant squared of x over 2. Okay, and then a 1/2 coming out from our chain rule, and then a dx. All right. So what I've got here in the numerator is actually equal to 2 du, and the denominator is 1 plus u squared. Okay, so let me stop scribbling and actually write this down. Okay, so this 2 I'm going to write out front of the integral, and then we have du over 1 plus u squared. All right, well, that's exactly the same integral we did last time after we made the u substitution. Okay, so I have the 2, and this is arctan, or tan minus 1 of u. Okay, or 2 times the inverse tangent of u, and our substitution for u here was hyperbolic tangent of x over 2. Okay. There we go. All right, now I've shown you 2 ways to do this, and there's a common error that can be made. Let me explain what is true here and what is not necessarily true. Okay, so what we did was our first version of this. Integral sec x dx. We found that was 2 inverse tan of e to the x. Okay, and then the second time around, we found that this was equal to 2 times the inverse tan of the tanh of x over 2. Okay, now often what people believe when we get something like this with indefinite integrals is that these 2 functions on the right-hand side are equal. Okay, I think if you make a graph of these, you will see that they are not equal. Okay, but if you remember kind of your basic calculus, okay, they do have to have a definite relationship. And if they are both otherwise correct as indefinite integrals, as antiderivatives, okay, they are not equal, but differ only by a constant. Okay? All right, so there's 2 ways to see this. One of them is actually, plotting a graph of those 2 antiderivatives, and you're going to see they have the exact same shape. They just have a vertical shift from one from the other. Okay, in other words, they differ only by a constant. The other way, which is a bit more laborious, but if you're looking for a good time on the weekend, you might be able to prove just analytically using properties of like an inverse tangent function, among other things, that they do indeed differ by just a constant. Okay, so I'm going to create some more space here in just a moment, and I'm going to show you the graphs, and that'll probably be as convincing as anything. Okay, here are the graphs of the 2 things that we obtained as antiderivatives of hyperbolic secant, and as advertised, they differ only by a constant. Okay, and in fact, what is that constant? Well, let's just see here. It looks like they differ by a constant of pi over 2. All right, so like I said, if you're just looking for a bit of a kind of an algebraic or a challenge with like proving some identities, proving that these 2 expressions, okay, when you take the difference of them, say this first one minus the second one, no matter the value of x, you always get pi over 2. Okay, kind of fun, huh? All right, so now let's go on and take a look at the antiderivative of the hyperbolic cosecant function. Okay, back now. So hyperbolic cosecant, we want to take the antiderivative. Okay, here it's going to be helpful to remember what the derivatives of cosecant hyperbolic and cotangent hyperbolic are. Okay, once again, we proved these in the video on the derivatives, number 3. Okay, so what I'm going to do here is I am going to multiply top and bottom of this by the sum of the hyperbolic cosecant plus the hyperbolic cotangent Okay, and actually I'm going to do one more thing. I'm going to multiply the outside by a minus sign, and I'm going to multiply this term in the numerator by a minus sign, like that. Okay. All right, so proceeding, negative on the outside. Now let me distribute this hyperbolic cosecant into the two terms in the numerator. So I've got minus hyperbolic cosecant squared x minus hyperbolic cosecant times hyperbolic cotangent of x over, okay, let me kind of interchange the terms in the denominator here. Hyperbolic cotangent x plus hyperbolic cosecant x. Okay, of course there's a dx at the end of all of that. All right, now if maybe you see what's going on here. I have two terms in the denominator, in this binomial in the denominator, and their derivatives live in the numerator. Okay, so maybe a u substitution here. U equals hyperbolic cotangent plus hyperbolic cosecant x. Okay, du then is going to be minus hyperbolic cosecant squared minus hyperbolic cosecant times hyperbolic cotangent. Okay, and then a dx on all of that. Okay, what we get when we do that is that this whole deal up here is a du, and the deal down here is a u. Okay, we've actually seen this already a couple of times in this video. So we have negative this time, but otherwise integral of du over u. Okay, so this is negative natural log u. Going back to the x variable, negative natural log of hyperbolic cotangent x plus hyperbolic cosecant x. Okay. Now there's that negative on the outside. What that negative can be used for here is to put a little exponent on the argument of the log function. Okay, the negative one. I'm not going to do that just now. I'm going to do something else first. Okay, and that is, I'm kind of on the fly here, I'm going to prove another identity. Okay, and it involves, you might say, double angle or half angle. All right, so let me start with the argument of the log, hyperbolic cotangent x plus hyperbolic cosecant x. All right, now the hyperbolic cotangent is really cosh over sinh. Okay, and then the hyperbolic cosecant is really 1 over sinh. Okay, so I can get a common denominator like this. All right. Okay, now what I want to do is use some double angle identities that we talked about maybe in our very first video back in number 1. Okay, and that is for the sinh. Okay, if this were like sinh of like 2u, then I'd get 2 sinh u cosh u, except in this case it's not 2u over here, it's x, so that means on the right hand side that's x over 2. Okay, in the numerator, okay, I think I used an identity for cosh x, like a very similar double angle looking identity. Okay, so I'm going to have x over 2 there, cosh of x over 2, so cosh squared, excuse me. Okay, plus sinh squared. Okay, so this part is that double angle identity for cosh x. Okay, all right, now inside this set of red parentheses, that is actually, you might say, kind of our very first fundamental identity, Pythagorean identity, for cosh squared, in particular of x over 2. Okay, so I have 2 cosh squared of x over 2 in the numerator. Okay, downstairs still the same, 2 sinh x over 2 times cosh x over 2. Okay, well I get 1 factor of the cosh to cancel out. Of course, the 2's cancel out. What I'm left with here is cosh x over 2 divided by sinh x over 2, better known as the hyperbolic cotangent of x over 2. Okay, so what I'm going to wrap this up as here is to say that the integration of cosecant hyperbolic x dx is going to be minus the natural log, and we just proved that that argument up here is really the same thing as hyperbolic cotangent of x over 2. Now in this case, I really am going to use this -1 as an exponent. Okay, so I'm going to take the reciprocal of the coth function, and that gives me the tanh function of x over 2. Okay, so this might be kind of a slightly cleaner way of writing it. Okay, integral hyperbolic cosecant x is natural log of tanh of x over 2. Of course, you know that you could always keep it that way, or maybe find a way of taking the reciprocal of that argument. Okay, that would not be a bad way of doing it if you wanted to keep like a single angle, so to speak, instead of going to x over 2. Okay. All right, so that's all 6 hyperbolic functions. All right. Hope that this has been helpful. Okay. Thanks for hanging around to the end. Thanks for watching. All right, and hope you enjoy these videos on hyperbolic functions. Give me a like and subscribe. Share with your friends, professors. And thanks for hanging out with me again for an episode of Derivability.